Welcome back, everyone. Today we are going to do an example of a confidence interval for inference, okay? You may remember last time we introduced the basic idea of inference for slopes called beta. That was our parameter. And our sample statistic was B, which is the slope of the regression line. And we also addressed the 5 conditions that have to be met before we embark on any sort of inference, whether it is significance tests or confidence intervals. The 5 conditions quickly were the concept of linear, that's Y has to be linearly related to X. We talked about the data have to be taken independently, so Li, and then N, normal, that for a particular value of X, the Y value is based on different sample sizes, different samples have to be normally distributed. And then those normal distributions for the same value of X have to have the same spread, which means they are of equal variance. And finally, the data has to be picked randomly. So that's where the Li, NER came from. So those are the 5 conditions. We're not going to go over them today. We are going to focus on step 3, which is to perform the calculation, and step 4, which is to draw a conclusion in the context of the problem. So here is the situation today. So imagine you have, 80 middle school students at various heights of a building, and they drop paper helicopters, okay? And each one of them, so they are at different heights, but each one of them is going to record how long it is taking for the paper helicopters to get down to the ground. So if you look at the bottom right-hand side, we have heights of those paper helicopters in centimeters and time it takes for them to get down to the ground, and that time is recorded in seconds. I'm assuming that the association is going to be positive because the higher the helicopter is, the longer it's going to take to get down to the floor. Okay? So how do we address the confidence interval? Well, the blueprint is exactly the same. We've been doing this over and over and over again. So we're assuming that this interval will capture the true parameter, right? Will capture the true parameter. What is this interval? It is the statistic. In our case, it's the slope of the sample, of this sample, okay? Plus or minus, because this is an interval, the critical value, it's either T star or Z star. In our case, it's going to be T star because we're taking a sample and we don't know the standard deviation. And then the standard deviation of the statistic. We used to say sigma of, let's say my statistic is X bar, okay? We used to say, well, it's either sigma of X bar or S of X bar based on whether or not we know the standard deviation. If you want to avoid this confusion here, because sometimes, let's say it's this one, we end up doing this, right? If you want to avoid this confusion, instead of using sigma or S, you could just use the word SE, standard error for my statistic. In our case, was X bar. So it might be sigma over root N, it might be S over root N, and that is based on whether or not the standard deviation of the population was known. So don't let this SE bother you. It is just the standard deviation. Don't let this bother you. This is just the standard deviation of my statistic in question. So we're thinking we want to compute, we want to be 95% confident that this interval will capture the true beta. Beta is the slope in seconds per centimeters of all the paper helicopters if we were to send, gazillion of them, okay? So You notice, as always, you need to know your statistic, you need to know your t-value, and you need to know your standard deviation of the statistic, called standard error. So there are three things we need to know. Two of them can be obtained from here very quickly. The first one, so look at this table. The most important numbers in this table are this one, and this one. In general, these are the three that you need to know. Sometimes we need this, but oftentimes you don't, and I'll explain. This is just R adjusted and R squared. Actually, they're both R squared. One of them is adjusted and one is not. So you don't have to worry about that. You don't have to worry about these four numbers at all. Okay? So what you need to know is this number, this one, and this one. And for our purpose, you just need these two. Okay, this is A and this is B. So we already know my statistic, 0.005. Let me write it down. So B is 0.0057244, okay? This is A. You don't need it because we're not looking for the regression line, y hat equals A plus BX, but that's basically your A, that's your B. And then this one, it's so hard to compute, but if a table is given to you, that is it. So the standard error for B is just this number, okay? Now, if it's not given to you, you could use this as, that is your standard deviation of your residuals, which is this. You know how ugly it looks? You have to find the errors, hold on, let me I don't want to confuse anyone. This one, S, is just like the sum of yi. In our case, it's time, right? It's time. This is your y. This is your x. So yi minus y hat over n minus 2. Don't forget to square these values, and then you take square roots. As you can tell, just to find S, which is given here, by the way, it's hard to find. And then you take that S, and you divide it by the standard deviation of X. So if you have a table for heights, generally you never have to do this, okay? If you have height versus time, L1, L2, this is your X and this is your Y, right? And you record your data, you just find one var stat and find S of sub F, standard deviation of this guy, right? And that is this one. So the standard deviation of the independence variable, in this case it's height, you hit it with square root of 79 because n is 80, and that is just your denominator of your standard error. The numerator is the standard deviation of the residuals. So you could tell that this is really hard to compute. Even if this is given to you, that is just this piece. Then you still have to find this one and hit it with square root of 79 and divide it into that number to get that number. So oftentimes we just give it to you, okay? The last piece we need to know is my t-value, right? The critical value. Let me erase this. The t-value can be found in two different ways, as you know. Just understand that t-value depends, it is a function of the critical, the CI, the critical, what is it called? My goodness, I am blanking out. And the degrees of freedom. The critical level, I don't know why I wrote I. Critical level. That's why I couldn't speak. And the degrees of freedom. So you can go back to the book, to the back of the book, pick the 95% confidence. That's your confidence level. And my degrees of freedom, in this case, and it is a long discussion, but for this chapter, the degrees of freedom is always n minus 2. There is a reason why we take off one more. We used to have either n or n minus 1. Well, now you'll see n minus 2 for a really good reason, which will take me a while to address. So you use 78 in this case. If you look at the table, let me enlarge for you. There is 60 and there is 80. There is no 68. But 68 is much closer to 60 than it is to 80. So I picked 60 and I picked 95% confidence level and I got 2, exactly 2. So of course this is not accurate because my degrees of freedom is not 60, it's 68. But that's the best we can do. So we could use 2.00. We know B, which is this number. We know the standard error, which is that number. And you should be able to compute your confidence interval, okay? Another way to find the t-value, the critical value, is just to do inverse t, right? And the area to the left of a 95% confidence interval is 2.5%, so you do 0.025. And this time you can be accurate and write 68, because that is exactly my degrees of freedom. Degrees of freedom is 70 minus 2, which is 68. And that is the precise value. And you put it in here, and you get t. So this is more accurate. 1.995 is more accurate than 2.000, okay? So I would suggest you use this one, of course. And you can compute your confidence interval. And, of course, step 4 is to draw a conclusion in the context of the problem. So we could say we are 95% confident that the interval from this to that in seconds per centimeters, this is a slope, okay? That's why the numbers are very tiny. In seconds per centimeters, captures the slope of the true regression line, that is called beta, relating flight time, and the drop heights of paper helicopters, basically relating these two. So that's how you draw the conclusion in the context of the problem. Now, if you didn't want to do this is, even though we use the graphing calculator to compute few things, this is the mechanical approach, the practical approach. You could use the TI and get all of this in one shot, okay? All of this, okay? And I wrote it here for you. So let's say the data is given to you. Sometimes it's not. If the data is not given to you, we would give you a table. If the table is not given to you, it is because we gave you the data. So you have height in centimeters. You put it under L1. Time in seconds. You put it in the L2. You go to stat, tests, and now you scroll all the way down to G where it says linear regression T interval. Don't pick test. There is a test right underneath. We're dealing with intervals, okay? And then make sure X is sitting under L1. Basically, your height is sitting here, not here. And your time is sitting here, not here. And you pick your confidence level, and you click on calculate. And not only that you get the interval, but you also get A and B and S and degrees of freedom, and even R and R squared for free, okay? So that's how you would find your confidence interval and draw the conclusion in the context of the problem. Now, remember, if this problem is given to you, you would need to check the conditions. Oftentimes, we say that 2 or 3 of those conditions are fulfilled for you. We just give them to you, but you would have to check the conditions before you perform the calculation. Let me just say one word on the standard error for B, which is 0.002018. It's a very small number. What does that mean? What does this mean, right? This is the standard error for the slope. What do you think that means? It means if we if we take 80 students and we did that, and we took another 80 and we did that, and we do it over and over and over, obviously we're going to get different slopes. Now, beta is the same. Nobody knows beta, but it is a fixed slope for the entire population of paper helicopters. But every time I take a sample of 80, and by the way, the sample sizes don't have to be the same. You know, today I took 80 middle school students. Tomorrow I took another 80 middle school students from another school maybe. Or I took 90 or 100. Obviously, every time I take a sample, I'm going to get a different B. Would you agree? Right? Just look at the three samples I did last time on the video. I had 3 samples, and each line was different, which means the slopes are different. Clearly, these slopes are different based on the sample that I picked. But beta doesn't change. We just don't know what it is. And that's why we're trying to find a 95% confidence interval. The way you interpret this, as we've done before, is if you take many samples, okay, the slope of the sample regression line would typically vary by 0.00002018 from the slope of the true regression line for predicting flight time based on the heights of the paper helicopter. How are these slopes varying from the true slope? On average, they vary by this much. That's what that means. Make sure you understand how to interpret the standard error for my statistic called B. All right. So this should conclude this short video, and I will assign a few problems. Take care. Bye-bye.